Hi everyone, so in this section we're going to talk about significant digits, sometimes called significant figures. First things first, anything that's a non-zero, which is the numbers 1 through 9, are always considered significant. So for instance, if we have a measurement of 253 grams, all three of those digits are significant. And we find the non-zeros like this to be pretty easy. It's these zeros that cause us all the problems. So here are the basic rules, and I would keep this handy as you work through first several chapters in the book, and you'll see that they kind of become habit to you as you work through it. Further, so zeros between non-zeros. So if you can kind of see that number there, the number is 10503. And where are the zeros that are between the non-zeros? And that's those two right there. So the rules, anytime it's in between, or what I like to call the middle, they are considered significant. So as I show you right here, this number 10503 has a total of 5 significant digits. Okay, let's erase that then. All right, going on to the next one. Sorry, I'm going to erase this so you can follow along a little closer to me. The next one is zeros that precede. So in other words, zeros that start the numbers. So see these two examples here? They have beginning zeros, or zeros that precede the first non-zero. They're never considered significant. They're simply holding the place or locating the decimal point. So as you can see right there, 0.003 has one significant digit, and 0.0108 has 3. This middle zero, actually again remember from rule 1, middle zeros are significant. Now, does that mean that 0.003 equals 3? No. It's that these are beginning zeros. They're holding a place. And in fact, when we get in a minute to scientific notation, you will see that you could actually write this as 3 times 10 to the minus 3. That makes it a little more obvious that there's only one sig fig, okay? Because these beginning zeros here were placeholders. All right, going on to rule number 3. Let's erase this. Rule number 3, and that is that zeros that are at the end of the number, if that number includes a decimal point, are significant. So zeros at the end, so you can see a whole bunch of examples here, and then whoops, I didn't circle quite the whole thing, but the numbers at the end. So 0.600, this beginning zero is not considered significant, but because there's a decimal here, the ending zeros are. So this particular number has 3 sig figs. And you can see how it works from there. Again, it's got to have a decimal point to be considered significant. In fact, this has lost its decimal point. That should be 10 point, like that. That would be 2 sig figs. And then rule number 4 actually kind of ties into rule number 3, and that is talking again about those ending zeros where there's not a decimal point in the number. So just 100 without the decimal, the only significant digit is that first 1 there. Again, that doesn't mean 100 equals 1. That is not what we're saying. But again, if we were to write this in scientific notation, you would see very easily now, oh yeah, there's only one significant digit. Now, how would I write 100 if it had a decimal in scientific notation? Well, it would be 1.00 times 10 to the positive 2. 100 without a decimal, you get 1 times 10 to the 2. Do you see the difference? Now, what's the difference in terms of, a science lab? Well, or even just a number. Let's think about maybe your bank account. 100. If I asked you how much money was currently in your checking account, you might say, I don't know, around $100. I would write, $100. Or maybe you say it's exactly $100. In fact, let's add the cents there and everything. This would be, exactly how much you have, and you're telling me exactly what it is. This is you're estimating, it's around $100. This is exactly 100. See where I'm going with that? And then finally down here, what I've been just talking about, again, To me, it's a little easier to see how it works if we're talking about scientific notation. And that is, with or without the decimal depends on with or without the decimal. Was it 100 without a decimal? Then it just becomes 1 times 10 to the 2. Was it 100 with a decimal? Well, then you can see where we go from there. All right, how about in calculation? Students seem to really struggle with performing calculations in significant digits. So if we're doing addition and subtraction, there's one set of rules. If you're adding numbers, you look at numbers past the decimal. So 12.1 plus 13, the answer would be 25.1. However, you look at numbers past the decimal. So in other words, 12.1 has 1 digit past the decimal, 13 has 0 past the decimal. You go with the lesser of the two. So my final answer here needs to be rounded up or down to match that lowest number past the decimal. So the answer would just simply be 25. Now, multiplication and division, a little different, and that is how many total significant digits. So for instance, 1.0 times 3. I'm going to make it an even simpler one. 1.0 times 3 is 3.0. However, again, before we finalize our answer, this has 2 sig figs, this has just 1. You go with the lesser of the two. So my final answer should just have 1 sig fig, which means the 0.0 has to drop off, and the answer would just be 3. So again, addition and subtraction, you look at numbers past the decimal. Multiplication and division, you look at total sig figs. Now, what if you have a problem? I don't have any examples here, but what if you had a problem where you had to do a bunch of things, like 5 plus 2 times 10.6, and on and on. Let's say it was a long problem. It wasn't just a one step. What I do, put everything in the calculator that you need to, and don't forget your order of operations, so things would have parentheses and such. Put it all in your calculator, hit equals, and get some big, long, crazy number probably, and then go back through and say, okay, well, what does my final answer need to have? Well, again, go back through and look at your rules, number of decimals, or number of total sig figs, and then simply apply that to your final answer. Okay, scientific notation. Again, I'm going to kind of do a quick refresher. This should be pretty simple. Hopefully you're remembering back to your math days. I showed you an example in the beginning. Basically, you've got a number, decimal, number, typically. Again, this is going to depend on those sig fig rules we just talked about. And then it's times 10 to the positive or negative, and then another number. Lots of numbers there, right? And this positive or negative depends on whether you're talking about a really big number. I like to think of it like that would be a really positive thing if that was my bank account. Oh, balance. Oh, can you imagine? It's probably like Bill Gates' bank account balance. Or if I had a really tiny number, that would be a negative thing. Ooh, not so good. So when you take a big number and you reduce it into scientific notation, you will see that the exponent, let me erase that there, see how that's times 10 to the 10? Positive 10, because that's a big number. And when it's a little number, like this guy here, your exponent is, what is that? Well, it's negative 10, all right? And it's just about how many places you've moved the decimal. So for instance, again, you can read through this example here too, but if I have 1.00 and it needs to be times 10 to the third, let's say, that means I need to 1, 2, 3, put my decimal there, fill in any blanks that we have. So 1.0 times 10 to the 3 is actually equal to 1,000. Now, what if that was, let's change it up a little bit. What if that was 1.00 times 10 to the minus 4? Well, again, I always start with the number that's given here, and then I move in my decimal. 1, 2, 3, 4, put the decimal there, and fill in my spaces with zeros. So that looks kind of ugly. Let's make it a little nicer there. So that's what that would look like. 1 times 10 to the minus 4, and because it had these 2 zeros after the decimal, that decimal is important. I'm going to keep those 2 zeros here. See how that works? All right, and going on here. The metric system, this is a system for conversions. So these are our base units and their abbreviations. And the metric system is great because it uses prefixes like kilo or milli. And it doesn't matter if you're talking about any of these things, length, mass, temperature, time, these prefixes are all the same. So for example, oh, actually you can see it right here, sorry, I won't even rewrite it. 1 kilometer, or we say kilometer, is 1,000 of the base unit meter. 1 kilogram equals 1,000 of the base unit gram. 1 meter equals 1,000 of the base unit. Oh, whoops, I went to milli there. So hang on, let me show you. So 1 kilo of anything equals 1,000 of that base unit. And again, that could be meters, grams, seconds, whatever. 1 base unit equals 1,000 milli-x. So in other words, kilo is real big. So think about kilometers. We drive distances in kilometers. Meters are things like a meter stick, which is almost equivalent to a yardstick, but you get the idea. You've seen a yardstick before. So that's like how tall we are. And then down here, if we come to the little units, if we're talking about millimeters, again, if I assigned all of this in terms of meters, kilometers we drive. If this was just meters, this is like how tall we are. We're not 1,000, but you get the idea. And if this was a meter and this was a millimeter, millimeters are tiny, tiny, tiny little increments. In fact, there's 1,000 little increments on a meter stick. So they're really tiny. It's like, try to think of a good example. Like your fingernail. The length of your fingernail would be measured in millimeters, not the width of it even. Well, you could measure the width as well, but the length of it would be just probably 1 or 2, unless you've got really long nails. How do we convert? Well, you've done conversions before, like down here. You could tell me how many dozen donuts is equal to if you have 8 donuts. Conversions are easy. You've done them. You've been doing them your whole life. Now, in chemistry, you're going to be working with units maybe you're not familiar with. For instance, if I had something that weighed 5 pounds, how many grams is that equal to? And if you have to convert that, what you'll notice is I set it up just like I set up this conversion here. What unit I want to get out of, I put on bottom. What unit I want, I put on top. So I'm going to get rid of pounds because the question's asking for an answer in grams. And when all is said and done, I'll have grams. And look at these two things, they're set up exactly alike. Now, what's the difference and what makes this much more difficult for students typically? And that is where the conversion factor comes from. Everybody should know that 1 dozen of anything is equal to 12, right? 12. Well, you might not know how many grams are in a pound. That's okay, you look it up and you find out that 1 pound is equal to 454 grams. So just because you don't know it in your brain, you don't have it memorized, you may have to go look it up, but notice it works the exact same way. 1 pound is equal to 454 grams. Just like 12 donuts or 12 individual anything is equal to 1 dozen. You multiply if it's across the top, so 5 times 454, and then you divide if it's on the bottom, which is just divided by 1, and you get your answer in grams. So don't panic. It's, again, you do something that you know how to do, and then do something where you know how to do it, you just might not have the conversion memorized. Here's some more examples, and then these are those metric system prefixes. Metric system prefixes. So lots of examples, they're all over. Take a look at this when you get a chance. Again, here's another. Now notice, this is a little bit different conversion than what I had before. On the previous page, I said 1 pound is equal to 454 grams. Here, I've got 1 gram is equal to 0.00220 pounds. Well, guess what? They're actually equal to each other, and that's okay. Just like sometimes you might see 1 meter is equal to 1,000 millimeters, or you might see 1 millimeter is equal to 1 times 10 to the minus 3 meter. It's just a matter of decimal and, which you're setting equal to 1. So don't panic if you see it listed 2 different ways. You can do it either way, use either one of these conversions, Just don't mix them up. Don't use a combination of them. Use either one and you'll get the right answer. And again, just last but not least, some other examples I'll kind of leave you with here. So don't be afraid to try these. Again, I always tell students, go back to what you know. Do a conversion of something you know, whether it's 6 inches equals how many feet. You could all do that, right? Or how many dozen, if you have 34 tires, let's say. Wow, sorry. If you have 34 tires, how many dozen tires is that? Now, it's not a whole number, but that's okay. You guys could do that. You apply the same process up here. Again, it's just a matter of where these conversion factors come from. Do you have them memorized and you know it? Then it's probably pretty easy. This, you guys know this, right? 1 foot equals 12 inches. And 1 dozen is equal to 12, whatever it is, tires here. And that's the only reason that this is easier, typically students think, than this, is because you know these conversion factors in your head. You don't have to go look them up. And if you have to go look them up, big deal. That's fine. You go look it up. That's okay. But you apply it and work it out the exact same way.